let's welcome the first speaker, Professor Jong-Wan Kim from GIST in Korea. So, Jong-Wan, the floor is yours. Thank you.
Okay, thank you, Eric. And good afternoon, everyone. So I'm kind of 3 hours, ahead of you. Yeah, still, at 5 p.m., just past 5 p.m. in here in Korea. And okay, unfortunately, I cannot be there with you, but let me try to deliver my listen to work on this digital twin-based cloud, something like that. Well, anyway, the full title is like this: APC, high-performance computing, and AI, and high-performance data analytics. I usually call them as a trident anyway. Then cloud-native computing. So I'm talking about cloud-native cloud, today. And the four digital twin-based AX. So you may curious what is AX? AX stands for AI transformation. So, okay, I think you got it. Okay, let me switch to the first page. So the first thing I just mentioned the HPC and AI HPDA. But if you see the kind of say slide in the center, you will see some kind of trident. So in the middle, we have AI application learning, right? And then in the left hand, high performance computing. On the right hand side, data analytics. So then in the bottom, you will see the kind of say this, how to say, sky blue color, the data lake. I usually call it data lake, which means we have to rely on some data accumulate, then you will work on AI. Also, you will also work on those data for your HPC and HPDA applications. So basically, this is something which I'm personally calling HPC, AI, HPDA trident. And also in the center, on the right-hand side, you will see this kind of say the logo for Kubernetes. I believe now this logo, I'm not sure whether you can see my cursor moving, but this logo is really famous, which stands for Kubernetes, which is actually cloud native, open source based, yeah, computing. Oh, that is kind of one message I have to say. HPC, AI, HPDA, cloud native computing, right? And also, similarly, I also let me mention about the left-hand side. You will see some kind of a term called iceberg and also open table format there. This is basically about how the data lake will have data, how the data will be stored and maybe organized inside there. Iceberg is another open source, maybe metadata related, also maybe ready for high performance data analytics. Then the word open table format is saying the format, this Iceberg's open table format can accommodate a lot of different data sets. I'm saying data set. Instead of a single individual data, we are calling as a data set, which means data set will have a metadata associated with individual data. So those collection of data will be accumulated. So our HPC AI, HPD Trident computing will leverage that. That's the main message I want to deliver. This kind of say, so structure or organization is really important. And so one more thing is I believe everyone knows cloud native computing is container oriented, Docker and so on, right? So that's also message is so shown in this diagram, the left hand side. Okay, I believe this is the main thing which I want to say today. Yeah, but this kind of say computing. Okay, let me say it this way. So everyone knows AI computing requires some very expensive GPU power support. But this GPU, maybe with other CPUs together, we don't want to have some separate GPU server, separate CPU server. Instead of having them, we want to have them in a pooled manner. Pooled manner is actually cloud manner, right? Cloud computing allows to utilize the CPU servers and GPU servers all together as a resource pool under the cloud, right? So that's kind of message I want to deliver today. Okay, let me move on to the next page. This is slide for cloud native computing, the definition of it, which is just I just mentioned the container oriented one on the bottom that you can see Kubernetes logo, container based. Then also Kubernetes is orchestrated. It's kind of cloud native computing, right? So container is very much yeah, important here because it's very portable, interoperable, also maybe scalable, yeah, under the cloud, right? Also, it also because it's scalability, it's very kind of say, if okay, performance versus price sense, it's very much effective. Okay, that's cloud native. And also another message which I also just mentioned about this data-centric viewpoint a little bit here. So data need to be accumulated in a manner that the accumulated data will be really ready to be consumed. Okay, here the sense of ready to be consumed data means the data, as you can see upper right hand corner diagram, the data will be kind of cleaned. Also data will be tagged so that we can identify individual separate data. Also, that can be through the pipeline, like this water pipeline. So we can easily consume it, right? So the sense of this one, it's the data need to be there, but when actually we want to use those data, the kind of action is so suppose we have some data, then someone may call it ETL, ELT. In the left-hand side, the bottom, we have the sense of ETL and ELT, which means you will extract some data from some kind of files or some collection of files. Then you may have to change it, transform a little bit because the kind of analytics you want to apply may require some kind of, say, format change or some kind of, say, okay, yeah, let me just call it some data transformation, which is some change into the extracted data, right? Anyway, that process is usually called ETL, but at the same time, if you switch the order of this, yeah, loading and transform, something called ELT processing means you may extract and then load data, then you will transform only after how you will utilize. So when some, which is actually the AI kind of training, for example, usually have the tendency of having the data kind of say a little bit loaded and then maybe analyzed or, okay, let me call it analyzed this way and that way because the training requires to consume some of data in this way or maybe consume data another way. So this way around, that way around. Anyway, try to kind of say train, right? You will utilize data for training, which means the data will be consumed for training. This this side, that side, all around, which means that exhaustive kind of training will utilize the data improperly. Okay. Okay. So far, yeah. So that is the beginning concept. Eric, any problem there or everything is okay there?
In
Okay.
please- yeah, please go on. Thank you.
Okay. Good. So let me continue. So I already mentioned what is AX, right? So AI transformation is kind of word, AI-based digital transformation. Here, transformation means something, it's total change, right? It's more than innovation, right? So actually the word transformation, I believe is popular. So I hope everyone there knows, I believe everyone there knows about this term. Also, another thing is I usually mention DNA, which stands for data, networking, and AI. Data and AI and networking, which means, okay, if you see the slide in the bottom, I have some kind of a say. Okay, so iconize AI thing, which stands for some small children, is a kind of say looking at the rainbow and dream AI is a kind of a logo name for this. So this AI model will be paired with all the data collected in the data dam. Here data lake, data dam, and through the water pipeline or data pipeline, that is actually networking, right? Data collected, accumulated through the data pipeline, which means actually networking support, then goes into AI. It's actually AI, it's symbolized as AI models. Okay. So that's DNA concept. So this DNA concept, actually, if we can add some words there, the data collected. Actually, data collected usually have the sense of some specific domain you want to have a data collection. So some specific domain, special domain data collection is more useful instead of having mixed up data collection for multiple domains altogether. This one domain data collection here, another domain data, all these domain data that will be networked together, right, through networking technology, which is also so symbolized as a data pipeline, I just mentioned, and then AI models or maybe AI tools. Also, I believe everyone now knows about the training and inference relationship, right? AI model will be trained and then will be utilized. Then that trained model, the result make the kind of summarized model or maybe trained model will be used for inferencing. But people are really can emphasize the need for, okay, this training and inferencing have to be kind of synchronized, which means when you do the inferencing, maybe some new data came in, then the model you have developed so far is not really kind of say not really kind of ready for this new version of data, some slight change of new data, right? So then you may have go back and then retrain yourself or fine tune your model. That training have to be done again, and then that retrained this AI model will be supplied to inferencing side, and then that will be used again, which means the loop between training and inferencing is important. So I'm personally kind of calling this relationship the AI should be live, which means training and inferencing should be related to each other, can be refreshed. Okay, that's the sense of live. Okay, let me move on. So same way, this DNA relationship is emphasizing the need for data delivered through pipeline, but actually in the sense of network, okay, just delivering data to another site. Okay, our hyperparameter network, like APAN and those, it's a potential kind of say where load wave to establish that. But the real problem is data is much huge size in case of this AI applications. It is actually stands for this kind of truck, data truck. Actually, the size of the data is huge, so it cannot be transferred from one location to another without some kind of say arrangement because it's not a movement of single data. As I say, full data set have to be moved from one position to another. So that is actually a little bit say highlighted in this slide. So the okay, if you want to kind of abstract all this relationship, in the bottom you may have this data collected, which is a kind of symbolize this yellow elephant named Hadoop is a kind of say moving the stored data, right? So, but this for data collection usually maybe carried out under the technical name or technology name of a data warehouse, data lake, or data lake house. So anyway, data will be accumulate and ready to be consumed. Then we have a cloud infrastructure for CPUs, GPUs, and maybe storage together. So which is running on the Linux operating system because most of the industrial kind of say computers are running over Linux, and also they are running in a kind of cloud manner, which is stands for hopefully cloud manner, which stands for natives, right? Then over this data and the cloud, then you have all those services available, right? This is again the concept for DNA, but infrastructure we have in the kind of which we may call edge and core, maybe the core side. We have a cloud infrastructure standing behind. Then we have end, which is all those machines, AI-ready machines. For example, the symbol in this one is like the box with the kind of say fields, which is kind of say which stand for all these autonomous vehicles running, right? These days, anyway, all those computers, yeah, in the end and or the edge, and then the core is actually governed by all these AI-driven yeah, applications, right? So through this, say, infrastructure change as well as say platform support over it, hopefully cloud native data-centric platform support over it may enable us to run any HPC, AI, HPDA application services, right? So that's full vision. Okay, so for this sense, the term cloud native HPC and AI, and in addition HPDA, but so in this slide, I'm trying to kind of borrow from the company with the green color. Everyone knows this company called NVIDIA, right? So they have been using this term cloud native supercomputing. So maybe cloud native HPC hyphened AI supercomputing is some kind of trend. Okay. Because when we are using kind of HPC and AI actually application learning, AI, everyone knows GPU is required. Maybe GPU which can run with compatible with the CUDA, something called CUDA, right? Say CUDA development kit, right? So those green yeah, GPUs, yeah, are actually supporting CUDA and it's also then, but if you go inside, okay, CUDA is say available, and then there is some name called so NIM. Okay, let me interpret the term NIM, NVIDIA inferencing models. But actually, NIM stands for containerized util. Okay, NIM. There's a model is AI model. AI model inferencing model will be contained as a containers. So CUDA ready containers. That's the name of a NIM. Okay, NIM is actually how all your AI applications or services will be composed of. It's container form factor, right? So that's one thing. Other things, I'm also trying to link with the digital twin thing. So digital twin it's actually something called the omnibus. I will also mention about omnibus, yet this digital twin and the Cosmos World Foundation model solve. That is actually the second part. Anyway, that company is working, promoting people to, okay, let's use some kind of CUDA ready GPU and then we have a NIM containers ready, which is kind of fine-tuned for all those, say, kind of say fine-tuned for very effective learning. Okay, because it's optimized for so CUDA enabled GPUs, right? Like that's the name component. Also, this Omnibus Cosmos component for digital twin and World Foundation support, and also something for LLM. LLM, you know, everyone knows LLM, large language models, but NEMO is one of the models supported by this company and NVIDIA company again. Okay, that is one picture, one typical picture. Okay, let me move on. So the sense I'm personally thinking, okay, how we can we really support AI application and services? But that AI application services may also need kind of high-performance computing support as well as high-performance data analytics support, right? But then also the aspect of kind of data accumulation, also maybe collection. So we have all those edge site, maybe the plant, maybe some kind of say harbor and like a kind of say a kind of city so areas. So then also maybe some what should I say? Okay, some some disaster area or okay, the term is not really correct. So anyway, plant or factories or some kind of say city part, there the data will be generated. Also, we will apply AI inferencing because the AI applications are really learning there. But when those models are learning, maybe some data, new data will be collected. Also, the model learning results will be collected. They will be merged, or they will be collected to central cloud. So which here I'm personally calling as federated AI cloud pools. They will be pooled together. So then this pooled data will be processed all together. But when you want to review this thing, you may want to see them through the kind of say scope or a kind of viewpoint of say this large O is actually digital twin viewpoint. So the sense this edge to exascale kind of say edge to exascale AI because when I say exascale, the scale on this federated cloud is really becoming larger than all the edge sites. Edge sites is will be small part of they will gather together and then will be supported one federated AI data center pools or AI cloud pools. Okay, that's the sense. So if we're continuing this, I'm talking about all this again, HPC-AI-HPDA, right? Trident kind of computing utilizing commonly accumulated data, right? When we are working on this, everyone is now talking about, okay, it's a good thing. It's good if you can do cloud native way of working with the HPC workload and AI workload and HPDA workload. It's a good thing, but the problem is the infrastructure is too costly, right? So the concept is I'm usually say promote this concept or how can you have some larger, say AI cluster or GPU cluster, let me say simply, GPU cluster. If you, the logic behind, if you really want to have a lot of kind of GPUs, actually GPU clusters collected or gathered together, okay, you may want to have thinking about some kind of common public parking slot. Okay, if you have this parking slot ready to be shared, a lot of people okay, you may want to park your car there instead of having individual private small parking slot because if you have more cars, this kind of common parking slot it will be useful, right? So this common parking slot concept, okay, I will park my car there, you will park your car, which means your GPU server there, my GPU server there, then altogether all more GPU servers will be available. Then the point here is so you may not drive your car all the time, 24 hours. You may drive for some time. Yeah. One day you will drive maybe 3 hours, 4 hours, right? But some other time your car will be parked without utilized. But if you enable sharing of your car with others, so it's carpooling or that sense, actually the way you want to increase, say, this very expensive AI GPU resource, the sense of cloud is a must. Yes, cloud allows you to do all this shared parking, but again, the sense of kind of collecting or kind of assembling all those cards together so that under the kind of say, agreement of let's share it. Also, let's share the facility together. Let's share the other things together so that we can save money to learning this. Okay, that is the concept I'm trying to, say, encourage you to think about. Also, one final comment to be added is all these AI data centers and all the GPUs, they are become very much big and bigger and bigger, also powerful, also which means more electricity. So now the single leg, say AI, okay, oh no, AI data center, very powerful single leg actually consumes more than 100 kilowatts per leg. Okay, that the cooling is no longer possible with the air, so we have to switch to liquid cooling. The liquid cooling needs some kind of another arrangement or may also very efficient utilization of AI in order to save the energy consumption and all other things together, right? So AI should be also applied for AI data center operation to save energy, to improve the kind of sharing efficiency of it very much expensive GPUs. Okay, then some kind of say the sharing concept is say spreading also data sense also as well as the resource sense. Okay, just some related slide for that. Also, the kind of diagrams showing that how all these clusters made, I believe everyone or APAN audience is already familiar with this kind of concept. But scale up, scale out, or recently some term called scale across is actually shaping up. And the example of this NVIDIA the GB200 is a NVL72 that contains 72 GPU node in one rack, consumes 120 kilowatts per rack, and so on. Also, I believe so this year at CES, Samsung and NVIDIA take the next version of this one called Vera Rubin thing again, MBL72, which consumes 20 out the two times more power than this one. This one consumes 120 kilowatts, but the next one is supposed to be yeah, running over 240 kilowatts per rack. Okay, it's a huge amount, right? Okay, anyway, the sense is it's really important to have a shared infrastructure, right? It's the concept of something I want cloud native computing will allow us to make this HPC, AI, and HPDA tried-and-paid kind of concept or shared, say, utilization concept possible. Okay, so that's something I want to highlight. I guess I consumed the 30 minutes. Maybe I guess I can use 10 more minutes. Okay, let me continue to say the second part, the digital twin thing. So the dream AI I mentioned about what do I mean by the word dream AI. Okay, it's a kind of catchphrase, and the digital twin is important there. So, so the diagram I'm showing one diagram, so which I'm trying to okay. So, okay, in our, say, school, graduate school, we also trying to train high schoolers or maybe some people who is entering into this. So we actually using this kind of model to concept here, which means AI models like LLMs, as you can see, dinosaurs, right? I believe you know, so GPT from OpenAI and the Grok from XAI, right? So those are kind of symbolized as, say, dinosaurs, also these large-sized animals like elephants and so on as transformer and maybe diffusion things. Also the basic ones like this chimpanzee and the monkeys and so owls and so on. Okay, all those models this abstraction seems useful when we say mention AI models are really diverse. Okay, the role of them, also the size of those models, right? this model too, I also recommend you think about this kind of, say, delivering message to kind of say audience who is trying to enter this AI space, maybe very useful. Also, the highlight on the data thing, data is important. Data here, also data engineering concept is not really well spread. But if you really want to, yeah, train your AI models, you will have to have a lot of data collected, right? But how you will utilize the data for AI training, it should be very systematic approach. It's not just kind of one time kind of say exercise. It's really like repetitive say exercise of kind of say making your AI models actually the ordered parameters, right? Over your kind of say LLMs, kind of growing or maturing, right? Okay. So that thing is also so does AI how to kind of say educate audience under with the concept model to maybe AI plan is a kind of interesting exercise, but we are kind of kind of successful with this approach to so kind of educate so some beginners for AI. Okay, let me move on. But this is the main thing which I also want to highlight today, digital twin, right? The way, the reason I'm emphasizing digital twin is, okay, digital twin. So it's kind of a good umbrella. Okay, so the abstraction which I just used the term umbrella, which means you have umbrella so then you can be like can free from all these raindrops, which means when you want to relate online simulation, okay, this is virtual one. Offline experiment is real one. The virtual and the real thing. So now the technology AI is you want to utilize AI for your real world problems, right? Real world domain specific problems. Then when you want to do that, how you will how much of those simulation effort will you utilize? How much real experiment, right? If you think about this relationship, everyone knows that simulation is taking less money than experiment most of the time. Also, simulation allows you to simulate some unrealistic scenarios. Okay. For example, dangerous scenarios for autonomous driving validation, right? So you cannot have a real accident, but when you want to very validate your kind of say autonomous driving AI models, so then but simulation allows you to that, right? It is good. It is good. So all this validate through online simulation repeated, you will move on to real experiment, right? So so I want you to think about digital twin, not just copying it's not like IoT, or it's not like AI assisted IoT. A lot of people sometimes kind of say confused about this thing. Digital twin, okay, it's mirroring of a real thing into the digital world. It's mirroring thing and its IoT sense value is mirrored, so it's say real world. Okay, digital replica of a real world is made. Yes, it's important, but the true value of a digital twin is relies on it's not real world. Even before you have a real thing to be constructed or built, you will design things, you will plan things, you will plan and you will design, then you will start constructing. But with those aspects of digital twin technology, you can do planning and designing, which is really showing the actual shape or actual operation of your twin, right? That is the value of digital twin. Okay, I think I made enough introduction on this, so I need to hurry for wrap up. Then, okay, I'm talking about the digital twin. Then, what kind of digital twin approaches are spreading? So something called OpenUSD based Omniverse is like taking momentum, supported by, okay, another, this green company called NVIDIA again. But let me just simply mention what is OpenUSD. The term open is open version of open source version of this, but USD stands for Universal Scene Description. It's like a 3D kind of graphics, kind of world type of description possible, originated from company called Pixar for 3D animation. So I think now with that, you can have the origin of this OpenUSD, right? Then with this basic description thing, which really kind of describe the world or make some kind of say target space you want to make into digital twin. Okay. So digital twin is now kind of say can cover manufacturing or all this say, let's say the delivery, right? Delivery or can I say data center operation, even the heavy, okay, all this shipbuilding, also all this Isaac simulation, robot simulation is also tied with this one. Anyway, that's scope. I believe you can either find out, say, so a lot of interesting material on this omnibus OpenUSD based digital twin thing. And so the concept, now my main point is how you will relate this kind of say digital twin approach for your kind of say domain specific AX kind of application. Domain specific AX means you want to apply this AI kind of say technology to, for example, mobility domain, which means smart mobility of all this car movement inside the city, right? Smart mobility service. Also, maybe you have some of this data twin based, all this mobility tracking, and so then your kind of say mobility AX applications or services are really supported by AI. Okay, let me continue. So if you see inside of digital twin, the concept is like this. You have a real world, and then this real world will be kind of say matched with or transformed into digital twin one. Okay. The aspect of this live AI may be linking because the mirroring of those real world into digital world has this liveness concept associated. Then they will be linked through something called the digital twin. This is green circle O. Okay. Then, but what is the actual digital twin data? So the sense of actual digital twin data is here. So twin data, right? Because all this mirroring data, it's data collection. So you have some kind of space and you have some facilities, you have some equipment, or you have a human inside that space. You will track every of those and will store their their kind of current location, their current shape, their current everything, right? That will be recorded. Well, using the structure of USD, then this is accumulated data will be utilized by this HPC AI, HPDA Trident thing. Then you can also associate with the physical AI technology. I believe you know this term, physical AI. Also, agentic AI thing. All these things will support you. Okay, so this is the whole concept diagram. Again, we have some example trial at GIST for this kind of space. We have our building, also our kind of data centers, small edge data, but which host top 500 supercomputer. Then they are digital twin enabled and so on. It's okay. So then also this one is will be supported by this cloud native cloud computing. Kubernetes-based computing, but Kubernetes multi-cluster cloud-native computing. So that's the message. And then, so all this support will be kind of maybe summarized this way. This is another diagram. So now this will kind of say something which I like, and I can finish it with this slide. Okay, if you see this one, okay, we have some kind of space. Okay, the space here, in the space, we have some kind of facilities. We have, say, computing equipment. Maybe we have humans, we have robots working together for some collaboration, for some manufacturing, some for other type of work. So let's call it in real world factory, right? Then we will mirror and observe this one into digital twin, and then digital twin accumulate data, and maybe this lakehouse based, so open source, okay, lakehouse based data collection is ready to be consumed for AI and HPC and AI and HPC and HPD, right? So then what it can allow us to do is this accumulated data gives a sense of how was the situation of this space in the past time, also now. From the past to current, so you have this modeling and simulation, but it's not really modeling. It's just kind of say replay of something already stored. But with this data accumulate, what you can do, you can apply AI models for this accumulated data over time, and then your AI model can make a prediction of a near future, right? So this is something called, say, MNSing happening, leveraging AI power. MNS had been there for, in the sense of a high-performance computing sense only, very numerically approximate the modeling and simulation sense. But now we are talking differently. All this accumulated data, so this twin data lake allows you to establish very good MNS with assist with AI. So they can also associate this live AI aspect. So, right, also physical AI aspect as agentic AI aspect. Also, maybe this observe, visualize, orchestration kind of concept, and as well as it's a foundation models, the world foundation model concept. Anyway, that's that full story. Maybe ultimate picture, we may heading ahead. Yeah. Okay. I think this final slide, let me skip this to some details message, and then this is the end of my talk. I guess I kind of consumed, yeah, around the 40, no, 40 more minutes, right? Okay, Eric. So,
Hello, everyone. I'm Eric Yan from Academic Sinica Greek Computing Center. I'm presenting about the Science Cloud delivered by my center in Academic Sinica in Taiwan. This is the program today, and we still have another session after the tea break. The cloud working group in APAN, we try to leverage the Science Cloud for accelerating the discovery, innovation, and also the most important thing is the collaboration among all the APAN members. So we hope to work together, not just among the partners, but also together with other APAN working group in different various application areas such as disaster mitigation, agriculture, and open and sharing data. So because all the application working group, they have to rely on some kind of computing infrastructure for the prototyping or pilot project or the collaborations. That's also the role the cloud working group could fit in. We also hope to supporting the capacity building, sharing our experiences to delivering the training, and sharing case study from all the partners, etc., according to the requirements from the partners. Yeah. Currently, the Professor Kim from Korea is the chair, and we have co-chair from Taiwan, me, and also Hiroki, the speaker in the next session, as the co-chair. Yeah. What I'm sharing today is about the activity we are working on. So Academic Silicon Green Computing Center is actually a mid-scale scientific computing facility. Mid-scale means the order of magnitude about 10,000 CPU cores, hundreds scale GPUs, and tens of petabyte disk storage for the scientific application, for the research and education purposes, in not just in academia silicon, but also for all the users in universities. Actually, we've been delivering such services from using cluster computing, grid computing, cloud computing from about 2005, been about 20 years. From 2023, we've been transitioned as a core facility funded by both the Academic Silicon and also the National Science and Technology Council, supporting the scientific computing services. The definition of the scientific computing here is very broad. Any computing requirements involving in scientific research, scientific application, and also educations are our scopes. Because we are providing a production services, so the reliability and efficiency are of the top priority in terms of the service quality. So we are serving as the computing arms for various user communities and also academic disciplines in Taiwan. The principal strategy is user-oriented and also collaboration-based service model. So we provide flexible and customized services for the users. The key value here is that we hope the scientists could focus on the scientific problems rather than taking care of the computing resources and also management of the computing facilities by his own, which might cost a lot of efforts and also money, for example. So we support the scientific workflow to be implemented in our computing facilities, and also support the performance tuning and also the workflow customization, etc. Currently, the application scale, as showed in the slides, that we provide the user with the 10,000 CPU core scale computing jobs, hundreds GPUs, as I mentioned. Yeah, and because the user has to pay for the services we provided, but the cost is affordable to almost every users in Taiwan. We also aligning all the services and support with the supercomputing center in Taiwan and enhance the advanced computing ecosystem in Taiwan. That's the long-term vision of this our core facility. In these slides, they are representing two primary user community here. In the left-hand side, that's the high-energy physics experiment community. They are the primary two user communities. So we support several high-energy physics experiments, from the Large Hadron Collider experiment, such as ATLAS and CMS here, AMS, the detector in the space station, and also the experiment of STAR, CPC, KAGWA, the gravitational wave application, LIGO, and also the future experiments such as EIC. So together with the Federated Instrumentation and the Detector Consortium, so we support quite well. We have created close collaboration with the high energy physics community in Taiwan. In the right-hand side, that's the structural biology community in Taiwan. They might using the NMR, the single-tone center, or the cryo-EM facility to get their data about the structure of the protein. And we are serving as the computing facility for the community. That means after the experiment, the data could goes directly from the experiment, such as cryo-EM, to the computing facility of our center, automatically on the fly. And then user could finish his data analysis, such as the 3D construction, such as the alignment, using the software they need just through the web browser without setting up any software in a user's computer. So all the flow, all the workflow, all the software, all the data workflow are designed by the scientists from the structural biology communities. So we integrate all the workflow by combining the two facilities together. So that's the typical model, how we support the scientific community in Taiwan. So through the, as I mentioned, the user-oriented and also very flexible collaboration models. So we support very easy access and also like tailor-made computing services for the scientists. So the vision is that we hope to facilitate the growth of the scientific computing ecosystem in Taiwan, which is composed by the user, by the facility, hardware, software, workflow, etc., and also the supporting team. We can manage the fast evolving technologies in hardware and software, or according to the user's requirements here. And here are the resources in our data center. We are running a data center, not a very big one, with 112 standard racks. So now we manage about 20,000 CPU core, more than 200 GPU, and more than 30 petabyte disk storage. About half of the resources are invested by our center. Yeah, the other half, that's collocated resources. That's procured by the user. They are collocated their hardware in our data center. In the long run, we hope their hardware could be shared, could be also part of our core facility, so that the hardware, the available resources could be growing. Yeah, that's also one of the collaboration model. In our own investment, because of the demand from the funding agency, in the past 3 years, we primarily focus on the CPUs. We hope in the next 2 years, with the consecutive 5-year investment on the hardware, we could reach about 10,000 CPU cores. Yeah, that's very new. So with this funding investment, we can retire those old and power not so power efficient hardware. So that's also another model for a stable operation. So after the 5 years, every year we could replace about 20% of the hardwares, and so that we could keep the most high performance computing facilities here. And in supporting the transition of the users, so we procure Intel CPUs in the first 2 years. From the third year, we now only rely on the AMD CPUs because that's the most cost effective in Taiwan. Yeah. So the same strategy is GPU. You see, we have many different generations of the GPUs here. because we don't have enough hardware money. But we still try to procure new GPU systems every year or every other years, so that the users could practice to understand what are the benefits making use of the new hardware, how to make better use of the new generation of the GPU. So from late 2025, we procured the Blackwell 6000 model, not the most advanced one as the Blackwell 200. Yeah. So the A100, that's the most high, in terms of performance, that's the best one because of very good double precision performance of these systems. And the new 6000, that's the new Blackwell architecture, which is very good for the AI applications. And also with the largest GPU memory on board, 96 gigabyte. A100, that's 80 gigabyte memory. Many AI applications, they rely on high, very good, large GPU memories. And we also have users need to have a 4 or 8 GPU at a time for their AI applications. In the CPU parts, we have users trying using 512 CPU cores for a job and more, but with more CPU cores for the job, the queuing time might be longer. Yeah, so that's the trade-off for the users. For the storage, as mentioned here, they are managed by the open source system, safe file system. That's a distributed and open file systems, which has been deployed in Taiwan in our center for more than 10 years. And in the past 10 years, we have 3 order of magnitude growth of the capacity. In 2024, we integrate the tape library system as the second tier of the storage system in our services, so that those dark data means very rarely used data, or just for the archive purposes, they could move from the online file system to the tape library systems and leaving those online storage systems for the computing in terms of the performance. And the power consumption is a challenge for us because we have to pay for the electricity cost. And monthly average, that's the kilowatt per hour, such amount, more than 200,000 every month, kilowatt per hour. Yeah. And because our data center has been about 20 years old, it's not a fancy one with the air cooling based cooling systems. So we now could have PUE on average, that's less than 1.6. That's almost the best we can achieve at this moment, unless we have big money to replace the cooling systems. Yeah. And here are some of the details of the hardware I mentioned. So let me just skip here. So the point here is that we keep on replacing hardware on both CPU, GPU, and storage every year. Yeah, that's important for our services. About the service architecture, yeah, we started from the worldwide grid systems. Since that time, we joined the development of the grid computing systems for the high energy physics experiment. And then we extended this core technology to support other scientific communities beyond the high energy physics. And then the emergence of the cloud computing and also the AI. So we build up the system architecture for those users, as I mentioned. So that's the basic idea. The other point is about the data and storage services. I mentioned the file system, which is a very big centralized pool for all the applications we support it, and also works very well in both the capacity, scalability, and also the performance. So we support the repository. And then based on the scholars application requirements, we also support the, for example, the GitLab, the CodeMD, those scientific communication and also application purposes for the collaboration, and also the research data management, such as the Depositor that's developed by the another institute in our academy, and also open source system like Zenodo, and also the mass storage system, including the backup and also the long-term archive. We also support the local data backup in the lab side or university side. That means we're supporting users to download data from our center to their own lab for another backup copy for the users. Because of the convenience for the users, so we support the job submission system using batch mode based on the Slurm, another open source system, which is quite common in many supercomputing center and services around the world. And also we build up the web-based systems. That's one of the cloud services. We call it software as a service for the users, especially for the life science communities. Yeah. For the WSCG system, that's totally different ways from the authentication to the job submission. Because in the worldwide grid, every user could access any data from any size and finish the analysis using any resources around the world on the worldwide web, on the worldwide grid, sorry. And this is the storage systems. You can find the details of the safe from the internet. Yeah, but the point here is that we've been serving the 13 petabyte scale with several hundred of core services for the storage system because of the performance, scalability, and also customization. And this is a typical ways to supporting the user applications. So normally, user could submit job either using Slurm or using the web, access data from the centralized storage pool. Yeah. The key point here is that the architecture is very simple and easy management. Yeah. So we support the Slurm high-performance or high-throughput computing services, and we support the integration of the user-selected software and also workflow. And we also support the application efficiency tuning and also customize the cloud services. And here's the example. We support the software as a service. For example, Jupyter Lab is one of the popular application here. That means just using browser, you can access the application or resources we provided. Now we've been supporting more than 70 such kind of applications. So each icon represents different applications. We also implement the AlphaFold applications in our systems. That's according to the, again, the structural biology scientist in Taiwan. Now becomes one of our services for the whole users. Yeah, and this is another customized user interface connecting the synchrotron center in Taiwan. Yeah. Of course, we are making use of the OpenStack and Docker. Sorry. Supporting the containerization and also the easier upgrade and also integration for the hybrid infrastructure and making use of the CPU or GPU hybrid computing resources in our center. Yeah. So we don't need to develop similar services as the commercial cloud. We just need to focus on the requirements from our users in Taiwan. So right now, we provide service models such as pay as you go. The PI will receive a accounting report, including the bill, on monthly basis, including all the details of the usage used by each member account. Collocation, as I mentioned, we also provide the buy-in. Buy-in means any PI who has the money for hardware, we could procure together using the same, not have to be the same spec, but we can we can get a better price for the hardware. And also service hosting as the depositor system I mentioned. We also support the resource reservation for some periods of time. For example, some users are required to join competition, which needs a couple GPU nodes in 1 or 2 months. Yeah. So the collaboration model is very scalable. And about the AI-enabled application or AI researches. In the beginning, we could only support the AI, the library, the framework for the AI applications, such as TensorFlow, Keras, etc. Because the development of AI system requires domain knowledge, which is not possible from our team. So that has to be done by the user community. Now we can also provide the AI application deployment. User could bring their AI program and we can help them to finish their AI application in our system, making CPU or GPU. And if the resources here is not enough, we can containerize the application and support the migration to another supercomputing center. And recently, we built up the model management system or inference management systems for the users based on the ML flow or QB flow of open source tools, etc. So in the long run, we also support the user to easier access to our services, to easy to integrate their computing models in our systems. So that rely on the research infrastructure and also application support services. So altogether, we can improve the service quality and also the capacity of the availability to the users. Yeah. So we hosted at least 4 training events in Taiwan in a year in different types. For example, the basic training, either for a 90-minute session or for half day or whole day. And we work together with the user community and supporting the semantic computing services. For example, we ever have a training session with the Taiwan University, and they have users that could share their experiences how to make use of our services to finish the high energy physics data analysis. We also hosting the international conference every year. Yeah. This is the conference I mentioned, IAGC. The next one will be held in mid-March, from March 16 for the whole week. So we have a keynote speaker from EGI, from ESNet, from the previous CODATA chair, and also from computational seismologist, yeah, and also from AI and quantum computing experts. So you are very welcome to join us in March. We also have the environmental computing workshop every year. So please check the details by the URL here. Oh, we also have the support from the security experts from Europe. So we will have a whole week a security workshop in the IAGC. And this is the information you can find, details of our services. Sorry, I only have 1 or 2 minutes. This is the second part of our center, which we involved in the international collaborations. That's originated from the high energy physics from the Large Hadron Collider international collaborations. Because of the computing is a essential role in the high energy physics experiment. So they have a working group here to monitor the relevant elevation in terms of technology markets and computing equipment, to understand the trends of the direction of the CPU or GPU or any computing components, and also the software technologies. Yeah, let me just have some example here. We have 2 reports in a year in the HAPIX computing. One of the trends will be reported and checked, such as here is the cost of the CPU. That's based on the statistics at CERN based in Geneva from 2005. And every dot means the cost, the Swiss franc to the benchmark system, HS06. So that's the performance per dollar, or the dollar per performance unit here. Yeah. So the trend here is that in the past 5 years, that's about 1.2, according to the ratio, and the trend seems going quite flattened, and the estimation to the 2030 is about probably 1.55. Yeah. Additionally, there's also the tracking of the storage cost, and also the technology, and also the trends of the market. And ARM CPU is another point which should be focused, because it's power efficient. Although it's not most performance efficient in comparison to the new CPU from AMD or from Intel. So you have to understand the features of the hardware, so you know how to make use of this. And the purpose here is that to optimize the deployment of such different types of hardware according to the constraints in each data center. For example, optimization of the power, cooling, and density, etc. So cooling becomes a very important factor while the growth of the data center. And here are examples of the commercial cloud making use of the ARM technology. As you know, the ARM didn't manufacture the CPU by his own. He licensed the design of the architecture and also the instruction set. Yeah. The other thing is that the carbon efficiency, because of the scales of the growth of the scale of data centers. So now it's identified that there are three scopes of the measurement of the carbon efficiency. Yeah. So you can find detail from these slides. The trend is that the immersive cooling is the most efficient way to cool your facility. And you have another choice, for example, using the liquid cooling. Before that, and rear door heat exchanger is also a choice. And from this table, you can see the cooling efficiency. Immersion cooling, that means the hardware is completely submerged in a liquid. Yeah. So it could achieve PUE less than 1.1 or even to 1.05. Yeah. And then the liquid cooling is the next best. Yeah. So in the long run, of course, we have to think about how to deploy the better energy efficient computing facility. For example, the optical I/O, optical computing system, probably quantum computing system in the next decade, the neuromorphic computing system, etc. And here is a roadmap from the Google, from the keynote speaker of IGC last year. So as I mentioned in the beginning, we hope to facilitate the regional collaboration in APAN and also extending to all the partners. Yeah. So that's the my report today. Yeah. So if you have any question, yeah, you are very welcomed. Yeah. I hope in the next session we could have more time for discussion. Yeah. Any quick question here? Yes.
Okay, so thank you for your presentations. And like you say that the trend is like the PUE must be less than 1.05, right?
By the emerging cooling.
Yeah. So what about your plan to your data centers? Because your data center, you say that like your data center's PUE is now about 1.5, if I understand
Yes.
correctly. So what is your plans next?
Liquid cooling.
Okay.
Yeah. But unfortunately, the cost is still a challenge.
Yeah.
Yes. Because now the liquid cooling rack is not compatible.
Okay.
Yeah, it's different vendor by vendor.
Yeah.
Yeah.
So
Still take time
oh,
to reach a agreement or some kind of ad hoc standard. Yeah. Otherwise, the cost will be quite high.
very hard. Yeah.
Yes.
Okay. Thank you.
Yeah. Thank you. Thank you so much. The next session will start it from 4 p.m. Yeah. Thank you. Thank you so much. Yeah.
And Eric?
Yeah. So Joanne.
Yeah.
So please help taking care of the next session.
Yeah. So I wonder, so my talk went smooth till the end?
Yes.
Okay, good. Yeah, good to hear that. Okay. So, okay. Hiroki, are you there?
Yes, I'm here.
Okay,
Yes.
good. So probably we'll just start with your talk, and then how many minutes are you expecting?
20 or 30 minutes.
Okay, you just have 30 minutes, right?
Okay.
You have plenty of time, as you can guess.
Thank you very much.
But yeah, so then probably it's better for you to kind of say, make you share your slide
Mhm.
before we start, right?
Okay, right.
Yeah. Then we'll resume at 7, right? 7. I
Okay.
think your time is 7, right?
Yeah. Thank you.
Yes,
Thank
so
you very
same
much.
for us. Okay, we'll see you
Thank you.
soon. Yeah.
Yeah, Joanne.
Okay. Eric, yes.
We have very capable technical staff here. They could support you to manage the session and also the remote presentation or any interaction such as Q&A.
Oh, I see. Yes. Actually, one issue I'm finding out, it's not easy to see the situation there, right? As you can guess. So maybe someone who may help us will be helpful, right? That's what I just tried to say, right?